Hey everyone, we're here for our next session. We have Ariel, Chief Scientist at Aztec. He'll be doing a talk on PLONK, and I'll let him take it from here.
Hello, happy to be here. You can only please some of the people some of the time, and this is an apology in advance. I sort of felt, since I've given a lot of talks on this subject in the last 6 months, I felt sort of guilty to repeat things too much for the recurring audience. So this will be a deep dive relatively fast. So apologies for any if it's hard to follow, and please feel free to ask questions. Okay. So let's start with what we've been calling Turbo-PLONK programs. So PLONK was a ZK SNARK we developed last year. And one thing, let me just check that. Okay. And one thing we noticed relatively quickly, and this is somewhat similar to the like air representations of Starkware, that instead of thinking of arithmetic circuits, it's convenient sometimes to think of these Turbo-PLONK programs where you have sort of this execution trace of rows where all these values, AI, BI, and so forth, are field elements. And this is like an execution trace of a program where we sort of how the program executes or verifies is that we can apply some local low degree constraint between the rows, right? So for example, for each row, we can check that like the next A is the previous B squared plus the previous C. And a lot of the power, the extra power you can get in PLONK and generally in this sort of pre-processing SNARK model is that you can also have these global sort of constraints. So which you can sort of think of as memory in some sense, that I can check, oh, is A 100 equal to D from the second row? So that was basically Turbo-PLONK, which some of you are familiar with. And what happened 6 months ago with this paper, Lookup, is that we saw that you can introduce in these programs this other operation, like in addition to these sort of global equality checks and low degree operations, you can introduce a lookup constraint. And how this thing works is you sort of pre-compute a table of legal desirable values, say a table of where each entry is like a row of 3 elements. And then you can simply have a constraint where I'm just checking, say, that the 5th row exists in the table. So and so you can think of, so what is this you can think of this table as, say, some function like SOAR where you have 2 inputs and 1 output, and the rows of this table are all combinations of legal inputs and legal output. So this is what we've been calling Ultra-PLONK, these sort of programs where you additionally have this lookup ability. So a brief history of lookups in SNARKS. So the first time, at least, I saw this idea was in this paper, ARIA, of several authors, mainly from UCL or all from UCL. What we did at Aztec earlier this year is a protocol for these enabling these lookup constraints with improved efficiency compared to ARIA. And very, very roughly, the sort of what is the cost of being able to use these lookups? So roughly it's, if you want to use a table of size t, like that's the number of rows in your table, and the size of the length of the witness where you're doing these, the length of your witness is w, roughly the cost of using PLONK is 2 times t plus w group exponentiations. So let's look at an example. A popular example is bitwise XOR. So, right, bitwise XOR is a common operation in hash functions, and say I want, for values A, B, C in my program, I want to check that C is the XOR of A and B. And so for a little bit of context, sort of the motivation, why is XOR a good example for, because right, sort of in SNARKS or STARKS, the operations we can do natively, efficiently, are these field operations. But here, right, with this bitwise XOR, it's very not sort of SNARK friendly, because right, there's no, if you have a huge prime field looking at the bit decomposition of elements and seeing if one element is the bitwise XOR of others, it's not something you can do with few low degree equations. You need to do all these bit decompositions and so forth. So sort of the direct way of using the lookup table approach for bitwise XOR is, let's compute a table of all triplets ABC such that ABC are all, field elements corresponding to 11-bit strings, and C is the bitwise XOR of A and B. And as I alluded to, the important question is, what is the size of the table? Because that is sort of the price that the prover is going to pay. And of course, we have to look at all these combinations of 2 inputs of 11 bits, so that the table is going to have 2 to the 22 rows. So that's one approach, and another approach that also I have to give credit, appeared in the ARIA paper, and is extremely useful, is using what's called sparse representations. So here, what we're going to do is we're going to construct a table of pairs, all the pairs A, AS, where A is, sorry, this should be 11 bits, but say it's a 10 or 11-bit string, and AS is A with zeros, with sort of, I'm sparsifying A, so with zeros in between the bits. So a simple way to write this, like precisely, is if A, right, the bit decomposition of A is like some AI times 2 to the I, then AS will simply be some AI 4 to the I. Okay. And yeah, please feel free to write questions. If something is very unclear, I'm looking once in a while at the. So let's see. Okay, so how does this relate to XOR? So the idea is that, say I've moved from my inputs A and B to their like sparse representation. At that point, right? So what is cheap for us? What's cheap for us is doing like field addition. After I've moved to the sparse form, I can get the bitwise XOR simply with addition. So what do I mean exactly by this? So let's look at an example. So say we just had 2-bit inputs, A and B. So this is A and this is B. So there, right? So here are their sparse representations. So I'm just adding a 0 in between each 2 bits. And now what happens when we simply add AS and BS? So in the first and third bit, we're going to get the XORs, right? Because right, if one of them is 1, I'm going to get 1. And if 0 or 2 of them are 1, I'm going to get 0, and maybe a 1 will be carried further. So if I look at AS plus BS, and now I'll look at the first and third bits, those will be the XORs. So that's the idea. But now, of course, so I need 2 tables. I need a table to go to the sparse representation, but now to actually get the bitwise XOR in the final form, I'm going to need to extract the values. So how does this work exactly? So my second table. So right. So if we look at this, we look at the addition result. Then if the coefficient of like the power of 4 is either 1 or 3, it exactly means the bitwise XOR is 1. So I'm going to apply a table from the sparse form and the addition result that basically extracts these these bits in the odd indices, and how that, maybe it's a little confusing, the formal notation here, but basically this is how it will look formally. It will be all the table of all pairs CS C XOR, where the CIs are now from 0 to 3, and I guess 3 is not, and yeah, and phi is sort of just this function that decodes the XOR, right? So if it's 0, sorry, the 3 is not totally necessary, right? If it's 0 or 2, it's like the XOR is 0. If it's 1, the XOR is 1. Yeah, so right, the point is, like, with this sparse representation, we could just make do with tables of size 2 to the 11 instead of a table of size 2 to the 22. And also a nice exercise is that actually this sort of thing, it gives us the XORs and bitwise ANDs at the same time, because the odd bits are the bitwise XORs, but the even bits are going to be the bitwise AND, right? Because if you have like 1 and 1, that's exactly what, like, when a 1 is going to be carried to the even. Yeah, okay. So so that was bitwise XOR, and now, and again, I apologize because from the size of the audience, this is probably a little too much in the weeds, but I'm going to show you sort of how exactly we use this for SHA-256. So if you think of SHA-256, right, there are these rounds, and in each round there's these two kind of heavy operations. And one of those two is, we can call it the majority prime, the Maj prime operation. And what is majority prime? So its inputs are 32-bit A, B, and C. And to define it, let's use this symbol for the right rotation of 32-bit values. And now Maj prime is this complicated thing. I take my first input A, and I do 3 different right bitwise rotations, and I XOR all of them bitwise. And then I take all this thing and I bitwise XOR it with the bitwise majority of A, B, and C. Right. So how do we use sparse representation for this this thing? So the idea is to map A, B, and C into this 16 sparse form. And now, suppose we had, and I'll address this in the next slide, but suppose we magically, someone gave us the right rotations of these 3 right rotations of A that we need. Suppose someone was very nice and gave it to us. Then the nice thing is, you can simply now, with this addition gate, we can simply do this thing. We look at 4 times just the addition, field addition of these rotates, plus just the addition of A, B, and C. And we do this right after we've moved to this 16 sparse form. And now the cool thing is that this addition result is injective enough to retrieve the output of majority prime. Why? Because, right, it's not, obviously this is not an injective map, because if I switch the values of A and B, I'll get the same thing because addition is symmetric. But the point is that for like bitwise majority of A, B, and C, I just need to know for each like bit how many of those 3 are 1. And similarly for this bitwise XOR of the 3 rotations, I just need to know for each bit how many of them were 1. And because I'm in this 16 sparse form, and I'm multiplying the addition of the rotations by 4, then this like addition will have those 2 bits of information. How many 1s are there in each bit of ABC, and how many 1s are there in each index for the 3 rotations. let me take a brief look at the, I think there was a question here. A useful technique is to use a different base. How is it 2 to the 11? Oh, I think Dara is right. Oh, I think, well, the table to go to the sparse form is 2 to the 11 because there's only 2 to the 11 inputs. But yeah, it's true that, like in the first example, oh no, so oh right. But in the going back from the sparse form, yeah, it'll be, yeah, the table size is 3 to the 11. That's a good catch. Cool, thank you. Yeah, it's a good catch. So, and I think I'll probably have a similar base mistake in the next slide. So, right, so one thing left to do. I sort of said, suppose someone was really nice and gave us all these right values for the rotations. So how do we get the rotations? And sort of the, yeah, and so sort of just to give a motivation for what I'm going to show, let's go through a more straightforward use of tables. So the more straightforward thing would be to slice up A. We are going to slice up A also, but to slice up A into these, like, say, parts of 10, 11, or 10 bits. And now for each slice and for each possible rotation, sort of have a table that tells you, well, what is the contribution of this slice under this rotation? So that will give you like 9 tables. And the sort of what we're going to optimize is, instead of doing this with 9 tables, we're just going to have another two tables. Well, really only specifically for the rotation stuff, it's only going to be in one more table. So let's see how exactly we're doing it. So I'm going to split my 32-bit A into limbs of 10 bits, that's the most significant bits, 11 bits, and another 11 bits. And now I'm going to, okay. So like I said, the idea is we want to compute all these rotations. So we can think of that we have these 9 rotation contributions we need to add up. So, right, because we have these 3 limbs, and each one under each rotation, right, contributes something to this terrible thing. Right. But sort of the little thing here to notice is that, in a sense, we only have 2 non-trivial contributions. And that's sort of the one where A1 is rotated by 13 and A0 in the rotation by 2. What do I mean by non-trivial? So, for example, I mean non-trivial, I only sort of need to look at the combination of rotation and limb, where the rotation sort of doesn't fall in a continuous segment. So for example, right, A2, it starts at bit 22. I rotate it right by 2. Then all its bits are still like, right, they're going to be like from bit 20 to bit 30 or 29. But so that's sort of, in a sense, that's a trivial contribution, because I can just sort of multiply A2 by some factor to get the right. But say I rotate right, the right rotation. What does it do by 2? What does it do to A0? Then, right, I get this thing that there's this wrap, this non-trivial wrap, right? That A will, like, now I rotated right by 2, so it starts at the last bit at like bit 30, but or 31 if you're counting from 1, but then it like wraps and goes up to 8 or 9. Depends if you're counting from 0 or 1. So in a sense, there's only these two non-trivial contributions where the wrap doesn't fall continuously, but like the wrap is non-trivial. And these are these two cases. But really, when I look at the sort of what ultimate contribution do I get, I really, right, like rotating A1 by 13 and A0 by 2, it's because of how I chose sort of the limb sizes. It means that I only need the table that does this sort of rotation by 2, right? Because when I rotate by 13 the whole string, then sort of A1 I get it like it's rotated by 2, right? The two smallest bits went up to the. So so in total for this Maj prime, what do we need? We need the table that goes to this 16 sparse representation, but then we also need this. Well, we need it also for 11 bits, and we need it for 10 bits. And then we need the table that takes us back, that sort of decodes the result after we do the addition. Okay, so that's that. Yeah, so that's basically it. Thanks for listening, and I'll take a look at the questions. Yeah, let me know if when I should finish. I guess I have 2 or 3 more minutes. A question concerning motivation. I was under the impression that we search for algebraic hash functions because they fit. Now we are back to bit fiddling. What's the meaning of this? So I guess the advantage of staying with the, I guess, yeah, there's 2 approaches here. One is to go sort of to the SNARK/Stark friendly hash functions. And then you don't need this bit twiddling. But right, I mean, there's no free lunch. The Stark friendly hash functions were designed in the last few years to be SNARK/Stark friendly, and some people could argue their security is not as well established or as the traditional hash functions. One may even go so far as saying that for a hash to be secure, maybe intuitively, if you need to do a lot of crazy things, and if you're not doing a lot of crazy unrelated things to be SNARK/Stark friendly, maybe you're not as good as a hash. So sort of I mean, there's definitely a few approaches here, but sort of our focus in Aztec is sort of bringing the snark to the things as they are, rather than the other way. Like whatever hash functions, whatever signature schemes people are using, let's try to get snarks to work with that. One very nice example, say just you want to use sort of the signature from your secure model in your iPhone. That's probably not going to be a signature on a curve that is friendly for snark operations. So that, let's see if there's, I guess I should finish, or yeah.
Yeah, if you have any closing thoughts, now would be a good time, and then we can transition to our next talk.
No, I think I said Yeah, that was a really good question for the closing thoughts at a more high level. So thanks for that. And yeah, I'm good. Thank you very much for listening.
Thanks, Ariel. This is really great.